Hi, this is Tarik Rashid. Today we are having an algorithm which is called Simulated Annealing. This is part one, part of the class of Advanced Artificial Intelligence. Now, um, let me take you through the algorithm theoretically. This is the first part, and the second part is coming later. So the first part, Simulated Annealing. Who invented simulated annealing? Well, simulated annealing was introduced or coined in 1983 by Scott Kirkpatrick and Daniel Gillat, Mario P. Vesey. These three people, they had a famous paper. The title of the paper was Optimization by Simulated Annealing, published in the Journal of Science. That was in 1983. So, simulated annealing, theoretical background of simulated annealing. Simulated annealing is a probabilistic optimization algorithm, so depends on probability. Sorry. Inspired by a physical process in statistical mechanics called annealing. So, annealing is a phenomenon in statistical mechanics. And which is the annealing process. It is originally in physics. So let's see what this annealing process is. Well, annealing is a technique used in metallurgy, is a subject. Metallurgy, there's a kind of material like metal or glass can be heated to a high temperature and then it cooled down slowly. During cooling, atoms rearrange themselves into a low energy, stable structure, and this process avoids defects and leads to a global minimum energy. So, all about heating a metal or a glass, that's the idea, the inspiration came from, to a high temperature, and then it cools down, and then during the cooling, the atoms in the material will arrange itself or arrange themselves into a low energy stable structure. So in optimization in this, because we are trying to get the best of the metal, so the energy, it can be considered as a utility function or objective function, and state is candidate solution. Minimum energy means that less in the states of material. So at less energy, it gives you optimal solution. So simulating annealing mimics this behavior. At high temperature, algorithm explores widely. Well, at high temperature, algorithm can accept worse solutions. But at low temperature, algorithm becomes more greedy, more stable to accept those better solutions. This helps avoid getting stuck in local minima, which is a common problem or issue in optimization process. So the core of simulated annealing is the acceptance probability. So probability equals E delta E minus T to the power that energy. That energy equals new energy, new state, minus the current. And there will be a decision rule. Decision rule depends on what? If delta E less than or equal 0 or 0 greater or equal delta E, that's a better solution because you need to have low as you can of delta E so that you can get a better solution. Now, if delta E greater than greater than equal greater than 0, then accept with probability P. Now, this allows control uphill moves, which is the key strength of simulated annealing. Now the temperature decreases gradually, okay? So in linear situation, temperature equals T capital minus alpha, and we'll come to alpha. What's alpha now? Alpha is a temperature cooling factor, okay? So geometrically, T equals alpha multiplied by T. So the T, new T equals alpha multiplied by current T. And alpha should be in the range of greater than 0 and less than 1. So that should be the value of alpha. So always by point something. A slow cooling schedule increases the chance of reaching global optimum. Now, convergence theory, SA is one of the few metaheuristics with theoretical guarantees. If cooling is infinitely slow, it converges to global optimum based on Markov chains and Boltzmann distribution. Now, relation to metropolis algorithm, SA based on earlier metropolis algorithm that was coined in 1953, developed by Nicholas Metropolis and his colleagues. This algorithm introduced the probabilistic acceptance rule used in simulated annealing. Now, why simulated annealing is powerful? Well, escapes local minima, that's the issue in optimization, works for nonlinear, discrete, and complex problems. For all these can work, requires minimal assumptions about the problem. Now, summary, inspired by physics, annealing, uses temperature-controlled randomness and accept worst solution with probability of this one. And algorithm invented in 1983 by Kirkpatrick and his colleagues. Strong theoretical base in probability and thermodynamics. Thank you very much for this, joining this session. Next session will be a practical example on simulated annealing. Thank you very much.